Hello. So 3 substitution methods today, or maybe 2.5, because one of them is educated guess. So 2 full methods and then kind of an extension. So Bernoulli substitution, right? It has this first bullet point here. To solve a differential equation specifically of that form. Notice it looks like a linear differential equation, but it has this one extra piece, right? That y to the n. If it didn't have that y to the n, it would just be linear, and we would solve it probably using integrating factors, right? But how do you handle that extra piece if you have that extra piece? You make this substitution, right? V equals y to the 1 minus n. Where does that come from? For now, I'm just giving it to you. I'm just saying this is a helpful substitution in this case. You'll see where that comes from actually when we do our primary source projects, from specifically from Leibniz, Bernoulli, and Euler. They collectively kind of arrived at that. So that's the first substitution we're looking at here. Note that after you make the substitution, you'll get a linear differential equation, which then you can solve using integrating factors. So it's the Bernoulli substitution doesn't fully solve the dE for you. It just brings you back to a linear first order dE, which then you can do by another method, namely integrating factors. 2, homogeneous substitution. If you can write your dE in that form, dy dx equals function of xy, where this function on the right-hand side satisfies kind of a curious property. If you substitute tx for x and ty for y, all the t's just disappear. That's what that's saying, right? And it's saying that the t's will all cancel out if you plug in tx for every x and ty for every y. That's called the homogeneous differential equation, and you can solve it using this substitution, y equals vx, right? I should mention what happens here. Then, again, it doesn't fully solve it for you, but the resulting equation will be separable, right? It's going to piggyback off of another technique that we already have, right? So that's what you can do then. You can do separation of variables, right? 3, anything else you feel like trying? So substitutions, you can do whatever you want. It's a change of coordinates. Make b equal whatever function of x and y you think might help. It's a lot like u sub, right? When you do u sub for integrals, a lot of times there isn't a guarantee that a particular choice of u will work. Just try one and you say, oh, hey, I did it. Or, oh, I got stuck. Let me try something else, right? So the same thing with differential equations. You can do anything else, right? Right. So in particular here, I want to look at these 3 methods, and I want to see which method applies to which of the following equations, right? So before I actually use the method to solve the differential equation, I just want to see which method applies to which, right? So first we have the Bernoulli substitution. How would I test that? Well, for Bernoulli, I'm trying to write it in this form. dy dx equals p of x times y plus q of x times y to the n. So let's see what happens here. So, well, what is that right-hand side? That right-hand side is, let's see, can I break it up a little bit? Sure. I could split it. It could be 1 over x, y, plus 1, plus x, y to the minus 1. It was almost Bernoulli, right? That 1 broke it, right? It would be Bernoulli if not for that 1, right? So that's what's the hold up there. Then we have, let's see, homogeneous substitution. So what was the trick there? The trick was replace every single y by ty, every single x by tx, and what happens? Well, a t squared factors out of the numerator and a t squared factors out of the denominator, and we're left with just the original. Those cancel then, right? And we're left with just the original function, right? We're left with y squared plus xy plus x squared over xy. That means that this method will apply, right? So yes, we are going to use this method. Miscellaneous? No, there's no reason to start guessing things because we already know homogeneous is going to work. Right? So there's an analysis of that first equation, each substitution method, and whether or not we want to use it. Now the second one, right, with a very similar process, we can actually see that that it is Bernoulli, because what do we get for the right-hand side? We have y plus x, y to the minus 1. This is Bernoulli, right? So we can do a Bernoulli substitution, right? So then, here, why would we do either of the other ones? We already found a nice, clean way that's going to work. The last one, you can try either of these. Try checking either of those. Nothing works. You can't get it in the form y times a function of x plus power of y times a function of x. So it's not Bernoulli. You cannot, if you plug in tx and ty for those, you can't just cancel out all the t's. They don't just all magically disappear. Therefore, it's not homogeneous. Miscellaneous. All right, let's try, I don't know. Let's try v equals x plus y. I'm just going to try the denominator. Why? Well, I don't know. That worked a lot back, but we could use some. Right? A lot of times you set u equal to the denominator, and it helps. So we're going to try the same thing here. That's our approach. So, all right. So now I want to show each of these how you implement, right? So let's do each of these. So let's solve equation A via Bernoulli sub, right? And the Bernoulli sub, of course, it's very hard to say that out loud, without imagining a deli and some special sandwich involving lots of capicola and prosciutto and all that, right? But I've been taking power series expansions all day. You got any Bernoulli subs back there? I'm starving, right? You want that's at least for me, that's the image it conjures in my mind. So let's do that. Let's chow down on our greasy Bernoulli sub, and let's make the recommended substitution, right? So what is the recommended substitution? Well, in this case, we have the B, equation B. There we go. Sorry, equation A is going to be by homogeneous. Equation B by Bernoulli sum, right? That was the big yes. So here we have n equals minus 1. Why do I know that? Well, because there's n, right? N is that power. And then what can I do from here? I sub v equals y to the 1 minus n, but n is minus 1. So we get y squared. V equals y squared, right? That's our substitution. If we're going to make this substitution, we're going to need to do more, though, than just that, right? We're going to have to actually, and this I should mention, we're just following this formula up here, right? So this, right? V equals y to the 1 minus n. We're just using that formula. So let's apply this to our equation. Now, a few things to notice. One thing is that we have to take a derivative, right? So differentiate with respect to x, both sides. Right, so on the left-hand side, I have just dv dx. On the right-hand side, we're going to do a little bit of power rule. We'll get 2y dy dx. Right. So that's the relationship that we're going to use. Not only v equals y squared, but also the derivative. Right? It's a differential equation. We need both, right? So let's plug in now to our differential equation. So I have that the dy dx, right? I know what to plug in for the dy dx now, because that is just 1 over 2y dv dx, right? And then I can plug that in on the left-hand side of the dE, right? So that's our left-hand side of the differential equation. Then what happens on the right-hand side? On the right-hand side, we have y squared plus x over y. So y squared is just v plus x stays as x over y. And I'm going to just leave that y as y because it's going to cancel with the y on the other side, right? So I end up with 1/2 dv dx, and then v plus x. Right. From here, my claim is this is linear, and we can use integrating factors, right? So clean it up a little bit by multiplying by 2. And then we have dv dx equals 2v plus 2x. Right. And then we can solve via integrating factors. Right. That process right there of solving by integrating factors, that's what we covered in a previous lesson, and we do the same thing, right? We subtract the 2v, right? Subtract that, and then multiply both sides by e to the minus 2x. Right, then you can collapse the left-hand side with the product rule and say this is just the derivative of e to the minus 2x times v. The unknown. Right, then we have on the right-hand side, it's just the same, right? It's 2x e to the minus 2x. Right. Now from here, you can actually integrate both sides. And notice you're going to need integration by parts, right? You have an x times e to a constant times x, right? This is going to use integration by parts. Okay. So I'm going to actually pause this video here. If you want to try that, you might be able to get it to work all the way through the end, right? Try evaluating that integral using integration by parts, solve for v using algebra, and then plug back in to solve for y, right? You should also be able to check your answer and see if it's correct by plugging back in for y in the original differential equation. Right? All right, so that's our part 1 of this little segment on substitutions. I didn't want this video to become absurdly long, so I'm breaking it up into another component. But I wanted to at least show the 3 techniques together, because I think that's one of the most useful discussions is, okay, well, given an equation, how do I know which technique to use, right? So I wanted to really feature that in this video. We'll continue the solving at another point, right? So you can see if you can solve the rest of this Bernoulli, see if you can do the homogeneous, see if you can do the miscellaneous substitution, see how those go. Right, great exercises. So, and you'll find the solutions. I'll present solutions in the next video. So, all right, thank you, everybody.